So welcome to my small talk about counting small induced subgraphs with edge monotone properties. This is all based on a paper that we sent to STOC this year. And let me quickly introduce my co-authors. There is first of all Daniel Marx, who is working at CISPA in Germany. Second, there's Philipp Wellnitz, who is working at the National Institute for Informatics in Japan. And lastly, there's myself, Simon Döring, and I'm currently a PhD student at Max Planck Institute for Informatics in Germany. So let me quickly give you some motivation and basic definitions. And this talk is all about counting small patterns inside large graph. So imagine that you have some social networks where the nodes represent people and the edges represent if people know each other. Then of course such a social network has a lot of pattern, and we would like to see how much these patterns appear in such a network in order to figure out some stuff about a network and compare different networks. One thing that we would like to be interested in could be something like how many celebrities are in some social networks, and from a graph theoretical point of view, a celebrity is simply a star. So in order to figure out how many celebrities there are, we can simply count how many stars there are, and then we can compare this with different social networks. A different example is from biology, and here we have protein interaction networks where the nodes are simply proteins and the edges are interaction between proteins. So in such a network, a click, for example, represents a so-called protein complex, and now we can study organism by counting how many protein complexes there are. So for example, we can count the number of 4 clicks here. And now the idea is quite simple. If we have an organism and we would like to study how this organism evolves over time, then we could just count how often these 4 clicks appears in this network and see how this number changes with different generations of this organism in order to study how this organism evolves over time. And of course, we cannot only count 4 clicks, but we can count all sorts of patterns and use this to study the evolution of an organism. And so the counting of small patterns inside of large graphs is useful in many different circumstances. We just saw an example on social networks, but they are also used in neural networks. They are used in biology and in database systems and in many, many more scientific fields. So this is a quite useful and general framework that is used in many, many applications. So let me quickly introduce this problem on a formal level. In this setting, we are given a graph property, which is simply a function on unlabeled simple graphs. And this basically just says if something is a valid pattern or not. So for example, if we use a graph property of being a star, then we basically end up with our first example in social networks. And if we use the graph property of being a click, then we get our second example from biology. So the problem is now defined as the in sub phi problem that gets as input a graph G and a number K and is asked to compute the following value, namely the number of induced subgraphs of size G with K nodes that satisfies phi. So basically, how often does this pattern appear in our graph G? And of course, for different graph properties phi, we get different problems, meaning that this is actually a quite large class of different problems, meaning that we can use it to generalize to many different counting problems. So this is actually a very, very general framework and therefore very useful to study. So let me give you a quick example. Consider the graph property of being bipartite and the following graph G and the number K is equal to 4. In this case, we'll look at all induced subgraphs of size 4 and see if they are bipartite or not. And if you see, in this case, there are exactly 3 bipartite induced subgraphs of size 4, meaning that here the answer is exactly 3. And of course, we could always compute the function in sub phi in this brute force manner. And this would take a running time of f of k times n choose k, because basically we have n choose k many induced subgraphs, and each subgraph we need size f of k to check if it's valid or not, meaning that we get a runtime of f of k times n to the power of k, basically. And this, of course, is extremely inefficient. So you can see that for something like k is equal to 15, this exponent is huge, meaning that for even graphs with some moderate size, this is not longer feasible. Instead of having an exponent that depends on k, like here, we would like to have an exponent that's independent of k, like here. So basically, we would like to get a runtime of the form f of k times n to the c, where c is some fixed number, meaning that the runtime does not explode with k anymore. This would lead to more efficient algorithm that can count small patterns in large graphs. So our question is now basically, can we achieve such a running time that has this form here? Is this even possible? And there are famous problems where it's widely believed that this running time is not even possible. Consider, for example, the click problem that gets as input a graph G and a number k, and is simply asked to count the number of clicks that appear in such a graph. And it's widely believed that such a problem cannot be solved in runtime f of k times n to c, where f of k is some arbitrary computable function. So it could even be something very huge like the Ackermann function, and c could be 1 billion, and still we believe that we cannot achieve a runtime of that form. And assuming the exponential time hypothesis, we can even show that you cannot achieve a running time of f of k times n to the little o of k, which means that our brute force approach that we used from before doesn't look too bad anymore, because that has a running time of f of k times n to the k, meaning that it's actually quite close to this lower bound here. So basically, assuming ETH, assuming the exponential time hypothesis, which states that basically SAT cannot be solved faster than exponential time, we get that we cannot be much better than the brute force approach. And of course, if we define our phi to be the graph property of being a click, like in this example here, then this problem, the in sub phi problem, is just equal to the click problem. By definition, they're exactly the same problem. So in this case, we see that this in sub phi problem is exactly as hard as click. And in general, we would like to answer the question, when is this in sub phi problem at least as hard as the click problem, since this would give us some strong theoretical lower bounds like this one here. So we would like to answer this question, and being equivalent to click in this manner basically is also known as being sharp W1 hard. So when is the problem in sub phi actually easy? The problem in sub phi is quite easy if the function phi is just constant on k vertex graphs, because in this case, this basically means that the output is either 0 if the function phi is constant 0, or it's just n choose k if phi is just constantly true. So in these two cases, the problem is easy, and we say that this phi is non-trivial on k if it's a non-constant function on k vertex graphs, and it's non-trivial in general if it's non-trivial on infinitely many k's. And it's quite easy to see that if phi is trivial, then we can actually solve this in sub phi problem in such a running time by just checking if one graph is true or one graph is false. So in this case, the problem actually becomes quite easy. And there is a famous result by Kotepian, Dell, and Marx, which states that this in sub phi problem can always be either solved in this running time, so is in some sense easy, or it's always at least as hard as a click problem. So we have a direct dichotomy result, which basically splits this in sub phi problem into two classes of problems, namely easy problems and hard problems. The problem with this dichotomy result is that it's very implicit, and we don't have an easy criteria to decide which properties phi, for which properties phi this in sub phi problem actually becomes hard, and for which properties phi this in sub problem is actually easy. And in the following, we would like to know in which case we actually are. And this question was quite interesting to a lot of researchers. So this problem has some history. And in the first place, people like Jerome and Meeks tried to answer this question for very specific graph properties phi, and they showed, for example, that if phi is equal to the graph property of being disconnected, then this problem is actually as hard as the click problem. And later they showed that for the graph property, for all graph properties that are minor closed, meaning that if phi of g is equal to 1, then phi of g is also true for all minors, then this is also a hard problem then. Then in this case, int sub phi is also hard. And later people showed, and later Roth, Schmidt, and Wellnitz showed that this also holds if we restrict ourselves to monotone graph properties. These are graph properties that are closed under the removal of vertices and edges. And then Foucault and Roth showed that this is even true for hereditary graph properties, so graph properties where you are only allowed to remove vertices. And lastly, what we do in this work is to show the complementary result, and we show that this statement is also true if we consider edge monotone graph properties, meaning a graph property is edge monotone if phi of g is 1, also implies that phi of g is 1 for all edge subgraphs of G. So, for example, being isolated is an edge monotone graph property. So we basically show the statement that for all edge property, for all graph properties phi that are non-trivial and edge monotone, this problem in sub phi is at least as hard as the click problem. And in the following, we would like to see the techniques that are used to show our main theorem. So the main theorem builds on the following theorem, which was first proven by Dörfler, Roth, Schmidt, Wellnitz in 2020. Later, they published the result in 2022. And this is basically and this theorem that I've showed basically states that this in sub phi problem is at least as hard as a click problem if there exists a sequence of graph GK such that their tree width is unbounded and the alternating innovator of each of these graphs is non-vanishing. What's the alternating innovator? The alternating innovator is this alternating sum that goes over all edge subgraphs of G, meaning that's usually quite hard to compute. So if you would like to compute this, then we have to look at an exponential amount of edge subgraphs, meaning that it's very, very cumbersome to analyze such an alternating sum. And in the following, we want to show that we can always find these graphs with large tree width and non-vanishing alternating innovator to show that this is actually hard. We will not show that this is true for the complete graph, because if we would show this for the complete graph, then this would actually prove the so-called Andrea-Karp-Rosenberg conjecture, which is very, very hard. But we will show that there are nonetheless graphs with high tree width that satisfies this property. So how do we do this? Imagine that I give you a graph, in this case here the complete graph, and you have the task to compute this alternating sum in sub phi, this alternating innovator. What would you do? You would look at all induced subgraphs of some specific size, plug this into this value and see what comes out of this. And this is of course very, very cumbersome, so we have to find some structure in this problem. And if you look at the following induced subgraphs, then you might find a pattern if you look at them. And actually they are all the same edge subgraph. All of these edge subgraphs are exactly identical. They are just rotated version of each other. So we basically take a graph and rotate it a few times to get 5 direct copies of these graphs. And this is from a group theoretical point of view, you can describe this as a group action on the vertices, this rotation. And the important part is that all of these graphs are isomorphic, meaning structurally identical, meaning that they will all evaluate to the same value in this sum, meaning that if you take modular 5, they will all vanish in this sum here, since they have the same value, and then we have 5 pieces of these graphs, so 5 elements of these graphs, meaning mod 5, there are either 0 times 5 modular 5 or there are 1 times 5 modular 5. In both cases they are 0. So they are actually just vanishing. And this of course does not also hold for the graph, for this graph here, but also for this graph here. However, this also holds for this graph here. However, there are some graphs for which this is not the case. For example, for these graphs here, that looks like that, it's actually not a group of 5, it's only a group of 1, because if we rotate this graph here, we get the exactly the same graph. And we call these graphs, which are invariant, under rotation fixed points, because if you rotate them, you don't get any change. And of course, there are multiple fixed points. And the idea is now, since 5 is a prime number, we can use the orbit stabilizer theorem to show that these orbits that we just saw either have the size 5 or the size 1, meaning that if we take modular 5, only this size 1 graphs remain, meaning that we only end up with fixed points. So if we take the sum here and compute modular 5, then we only get these fixed points that we saw, which are far, far fewer than the other graphs. So this alternating sum becomes much simpler to analyze if we go over fixed points. And formally, if you look at all the fixed points that are possible for prime number p, then we get exactly the so-called circular graphs. These are graphs which are defined in this following way here with this edge set. And these are basically the graphs which are invariant under rotation. And you see here 3 examples of these. And you can also see that this example and this example together combined get this example here. So these fixed points here, these circular graphs, actually can be combined together to form another circular graph, meaning that they form some lattice structure, which you can see here. So here I just drew all of the possible circular graphs with node sets 7, and you see that you can just draw a line between 2 of them if they are inside of each other. And then you can see that this forms a lattice structure, a so-called Hessian diagram. And in the following, we'd like to analyze such a diagram here, because the main observation is that instead of computing this huge alternating sum, we only have to look at the fixed points each time. So if you would like to compute the alternating operator of this guy here, then we only have to look at these 4 graphs here, meaning that this makes our analysis much, much simpler. And now we would like to find again some graphs with high tree width that have a non-vanishing alternating operator. And you can actually convince yourself that a high tree width in this case basically means a high level. The level is just the number of fixed points that are needed to construct something. So you can see that I ordered this here in the level, and actually the level is a lower bound for this tree width here. So meaning that a graph of level 2 has tree width at least 2. So we only have to find fixed points of a high level with non-vanishing alternating operator. And we will use the following win-win approach to actually solve this problem. So in the first case, we assume that there is a fixed point with a high level that is actually true on phi, that satisfies phi. And we show that there is a fixed point of high level such that, and we basically then show that at some specific level, all fixed points will have a satisfying phi. And in the second case, we assume that there's no fixed point of high level that satisfies phi, and then we show that we can find a fixed point with non-vanishing alternating operator and high level by using some kind of linear algebra argument by building a linear system of equation. So for the first approach, let's look at a larger graph here. This is basically the Hessian diagram of size 13. Where n is equal to 13. And of course, if we have such a graph here, then it's not very meaningful to us because there are many, many different nodes. However, I colored graphs that are isomorphic to each other with the same color. And if we simply combine these graphs, then we get this much simpler diagram here. And now what happens if there's a 1 at some specific node here, for example, then we know that in this isomorphism group, all nodes satisfy our graph property phi. And since our graph property is edge monotone, this means that all edge subgraphs satisfy the graph property phi, meaning that this one propagates down here to these two graphs here. And these, of course, also propagate down. And now we see that at this level, all nodes satisfies our graph property phi. And you can convince yourself, since the graph property is non-trivial, we can just assume that there is a 0 at the top here, because if there would be a 1, then phi would be trivial on the specific number, meaning that we can find at some point a node that has the property that its value is 0 and all values below are just equal to 1. And this node is very specific, it's very special, because if we have such a node, then you can simply compute the alternating innovator using the binomial theorem, and it's now very easy to show that the alternating innovator is simply plus minus 1 modular p, meaning that if we have such a node, we are actually done. So the only thing that's actually needed to prove is that if we start high enough, then this propagation factor is fast enough such that this cutoff here occurs at a high enough level, meaning that we can actually find something which is high enough. So that's the thing that we will show in the paper. And for the second approach, where we have this linear system of equation, we just assume that all of the level at some points are equal to 0. And what we do is we simply sum up all of the phi values for one specific value level, and then we also sum up all of the alternating enumerators for one specific level, so call this wi and wi hat. And now we can just see that these are linear dependent to each other with some matrix C here that it's actually not hard to compute. And now the idea is that if we know that all of these here are 0, then we know that this part of this vector is just equal to 0. And what do we do is we just basically look at this submatrix here and show that this is non-singular, meaning that if this is not a 0 vector, then this is not a 0 vector, meaning that at this position here, we find something with high level, with a high enough level and non-vanishing alternating enumerator. And this is basically the second approach, how to show this. So we see that in both cases, in the first approach where we have something high, we have this avalanche effect. And for the second case, we have this linear algebra effect. And both of them are sufficient to show our statement, meaning that we can end up with the following statement, that if our graph property phi is non-trivial on a prime number p, then we can always find something with non-vanishing alternating innovator and level at least root of pi. And since root of pi is unbounded, this basically means that the tree width is unbounded and we are done for this case. Of course, this is not enough to show this case, because this only shows if phi is non-trivial on infinity prime numbers, and this is not what we want to show. Instead, we have to first go to prime powers, meaning that we have to go to finite fields, which is a very natural extension to what we just did. And we also need to go to a general number n, and this is basically by considering stuff like product groups and finding the largest prime number power inside of these product groups. And doing that allows us to show the statement for the general case, where we have only non-trivially on infinitely many numbers and do not restrict ourselves to prime numbers or prime powers. And this is showed then in our paper as our main theorem. And this basically states that if something is non-trivial and edge monotone, then we are at least as hard as a click problem in this case. And what we also show is that for the most part, if we are non-trivial infinitely many prime powers, then we even get these tight lower bounds under ETH, meaning that we cannot be much better than brute force. And of course, we have here the caveat that we need prime powers, but actually in some upcoming work that we are currently working on, we remove this condition and only need non-trivial anymore to show this tight lower bounds. We also are able to simplify our proof a little bit and do some other things, like showing that the problem is still hard if we go to modular counting. You might know that for some counting problems become much easier if you go to counting modular 2, for example. Famous example is counting the number of perfect matchings becomes easy if we count these modular 2. But we show in our paper that even if we consider this in sub phi problem modular some prime number p, then we cannot be faster than the brute force approach, basically, meaning that even the modular counting version of this problem is a very, very hard problem.